Today's videos are on resolution. So resolution, we're going to define it as the ability to distinguish between two different sources. Oh, and if you're watching this, two different sources of light, and you're actually listening to it, quick message. Shout out to Ben Vest. You asked if it was possible to have interference in 3 dimensions, and of course it is possible. Your teacher was being silly the other day and was thinking of it in the wrong way, but yes, it's absolutely possible. It happens all the time. That is really the only main way that interference happens, but I just didn't explain it well, and I was thinking of it in a wonky way. So I do apologize for that quick little shout out. All right, just want to give that to you. But anyways, moving on, we're going to talk about resolution, okay, the ability to distinguish between two sources of light. You have this image here, you have two car headlamps, all right, where we have the two headlamps being well resolved. In other words, the space in between them, we can see that, there are definitely two sources here. Just resolved, they're kind of joining together here, and not resolved, it could be one source. We're not able to tell really between the two central maxima, all right? So the ability to resolve light, it's going to depend on a few different things, okay? This depends on, all right, the distance from the aperture, all right? So in other words, how far the sources are from the opening through which the light passes. The second thing it's going to depend on is the distance or separation between the sources. Okay, if they're really close together, it'll be a bit more difficult to resolve. The wavelength of the light that we are observing, okay, that has to do with the diffraction through the aperture and the size of the aperture, of course. Again, dealing with the diffraction that occurs, therefore the interference. Okay, so what we see here, this is the resolution of light, all right, from two different sources through two different types of apertures. This is through a single slit here, and this is through a circular aperture, okay? Now through a circular aperture, circular apertures in the real world you can think of as our eyes, okay, our telescope, but we have two sources coming through it, okay? What we see here in this first image, I want to take a look, the diffraction pattern of a single source of light passing through a circular aperture produces this almost bullseye image, all right, of constructive and destructive interference, and that is the interference pattern you get. So what we see here are two sets of examples, all right, with the single linear slit and the circular aperture here. And what we see is that the interference pattern, all right, we have two distinct peaks here, two distinct peaks here, okay, two distinct peaks here as well, and here the peaks are no longer distinct, all right. Here, again, they're not distinct. That could be a single source that's not resolved. These two are definitely distinct, okay. So, moving on, all right. Actually, really quickly though, we have some examples of circular apertures. I said it, but let me at least write it out. Okay. Circular aperture. All right. The pupil of an eye. I said a telescope, and I think you can also consider a microscope, right? Same thing. So, the actual image, or pardon me, the graph of the intensity of the light, right? For a single source of light, okay, the interference pattern looks something like this. All right, and if it's going to be well resolved, the other maximum is way over here. Okay, actually, let me just do that again. Make it way over here. Okay. So it looks something like that. Okay, that's a well resolved intensity diffraction pattern there. All right. So for it to be not resolved, we have our image here again. Okay. What happens, all right, is that the maximum is going to be like somewhere over here. All right. Okay. So it lines up like this, and they're pretty close together. We have this condition, right, where it's just resolved, and the way that this is going to look. Okay. This just falls off here. Let me just redo this. All right. this is what it's going to look like, actually. And what we see happening here, okay, is these central maxima are going to occur over the first minimum, okay, of the other intensity pattern. All right, so our resolving power, okay, when we talk about resolution, is the minimum angle between the sources for them to be just resolved. This is actually the minimum angle between the sources and the distance from the aperture is really what this comes down to. All right, so for a single slit, right, this minimum angle actually comes down to this equation right here. All right, for a circular aperture, we're not going to do the derivation, but that equation changes, and it's theta equals 1.22 lambda all over b. All right, so that resolving power, that's what the theta is, and I'm going to show you how that's connected to the definition here in a second. The Rayleigh criterion, all right, this is for, or Rayleigh criterion, depends on how you pronounce it, for two sources to be just resolved. Uh-oh, smartboard's acting up, gotta pause it. All right, the glitch in the matrix has been resolved. So, for two sources to be just resolved, the first minimum of one diffraction pattern must be located or is located on top of the central maximum of the other diffraction pattern. All right, so what this is telling us is that that experiment we did in the hallway, right, where you're looking at those two little patterns of horizontal white and black lines, right, you're just going to be able to tell their separation, okay, when that interference pattern, the maximum of one lines up with the minimum of the other inside your eyes when you're looking at it, all right? So here we go. Here's the image that we're going to use, all right, to help us to understand this. So what we have are two sources together here, all right? As they move closer, theta is going to increase, all right? And so the separation of the central maxima is also going to increase. I'm going to show you what this looks like here. We can draw it in, and we're going to do a little bit of geometry here. Alrighty, so I'm going to use my spot tools here and do this properly, right? So we got the ray from one source coming in here. We're going to say it comes in, goes through the middle. It's there. There we go. Good. And then this guy. Okay, so it comes through the middle and hit that. Both there. Okay, beautiful. Okay, so the way that we're going to have to draw this here, right, is that the central maximum has to occur right above this point right here, right? So to have two of these guys be just resolved, what ends up needing to happen, let me draw this really quickly, all right, what ends up needing to happen, okay, is that condition right there, all right, where the central maximum occurs over the first minimum of the other interference pattern. Okay, there we go. So what we end up with here, all right, we have, this is the separation. Okay, so this is this dimension right here. And this is the separation between the sources. Okay, and the distance from the aperture to both of the sources. Typically, these sources are rather close. All right, so this distance you can take as being this guy right here. All right, and what we end up with here, okay, doing a little bit of trigonometry, what we're going to say is that this angle, all right, separating both of the sources from the aperture, we're just going to call that theta, okay? And let's see here. Theta, all right, when we're over here, is going to be this angle right here, and I'm going to explain why that is in a second here, okay? So just bear with me. It is the same angle. If you look at it, it's the distance from the center of the central maximum to the first minimum, and that is the angular half width. Okay, so that is theta as we've been talking about it so far. All right. So if we come over here, though, all right, what we see is that doing the right triangle thing, all right, tan of theta over 2, right? Since we're dealing with this right triangle that we've drawn in here first, all right, it's going to be equal to s over 2 divided by d. All right. Small angle approximation. Allows us to say theta over 2 approximately equal to s over 2 divided by d, divide both sides, or multiply both sides by 2, and what we're left with is theta is equal to the separation of the sources divided by the distance of those sources to the aperture. Okay? This turns out to be the same theta as for a single slit. Right? Theta is equal to lambda all over b. And for a circular aperture, theta is equal to 1.22 times lambda all over b. Okay? These are the angular half widths, all right, from basically the central maximum to the first minimum. Okay? That's that same distance right there as the thetas we've been talking about. All right? And that's pretty much it. We're just equating both of those thetas, and those are the types of problems we're going to be solving. So if we take a quick look at a practice problem here, all right, we have the brightest star in the winter sky in the northern hemisphere is Sirius, all right? It's actually a binary system, that two stars that orbit each other, and the Hubble Space Telescope, okay, which is 2.4 meters in diameter, is going to be pointed right at this star, okay? And this is approximately 8 times 10 to the 16th meters from the Earth. So the question is, all right, can the Hubble Space Telescope resolve them, or does it see both of them as a single point of light? And the other piece of information that you're given here, I'm sorry, is that the average separation of these stars is 3 times 10 to the 12th meters. So very quickly, all right, we have to make an assumption, and that assumption is that our light has an average wavelength of 500 nanometers, and this is true. This is the average incoming wavelength, okay, for the light coming in. And then, the other thing that we need to consider here, okay, is that what we need, the result, actually let's just write down all the variables that we have in addition to this. We have the separation is 3 times 10 to the 12th meters, 3 gigameters, and then the distance from the star is 8 times 10 to the 16th, which I guess that's 80 terameters. Yeah, I think so. And why am I wasting my time on this ridiculous exercise of trying to remember the prefixes? I don't know. Anywho, the angular separation that is needed to resolve these guys, all right, comes down to this, the ratio of these two dimensions. And so we would need, all right, for these guys to be just resolved with sig figs, 4 10,000ths of a radian resolving power. Turns out, all right, that with this telescope, our resolving power is much stronger. 500 meters. So those two stars in that system could be even closer. So our conclusion is that Hubble can resolve these stars. All right. What I would recommend to you, okay, is to read that back page. That's the last piece of these notes. All right. So there are 3 examples in which you need to be familiar with resolution. I will ask about one of these on the test. So understanding how they work will be very, very important. We will be talking about CDs and DVDs a little bit more in the next, in one of the future units, digital technology, but understanding this resolution idea will be good for right now, okay? It's the difference between regular DVDs and Blu-ray, all right, in terms of this idea of resolution here. Electron microscopes as well, and radio telescopes, that's the big one. That's what we took a field trip for last year, and hopefully maybe, I don't know, we'll see. We might do that again this year, all right? Take care. That's it for the notes for tonight.